Good morning, all of you. Welcome to Sri Jayendra Rank Zone. In the previous session, we have discussed about adsorption and also catalysis. In this session, we are discussing more about catalysis and also other topic in this chapter, that is surface chemistry. Now, we are going to start. So please listen carefully. We have solved so many questions regarding surface chemistry and adsorption topic. So those are all very important, and you can solve based on that concept. You can solve more questions also. Now let us start new concept, that is catalysis, more about catalysis in this session. Yes. So coming to catalysis, we have discussed about homogeneous catalysis as well as heterogeneous catalysis. Now we'll discuss more about catalysis in this chapter. So let us start now. Shape selective catalysis by zeolites. Very, very important. They'll ask this question in the examination definitely. So what are zeolites? Examples of zeolites. So this concept is very important. From this, definitely you'll get a question for competitive exams. So what are shape selective catalysis by zeolites? More about catalysis. Let us start now. The catalysis which depends upon the pore structure, pore structure of the catalyst and the size of the reactant and product molecules is called shape selective catalysis. The catalysis which depends upon the pore structure and the size of the reactant and product molecules is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb-like structures. Very important. They are looking like honeycomb-like structures. So that's why they can absorb many gases. I'm writing it clearly. So honeycomb-like structures is important here. So zeolites are good shape selective catalysis because of their honeycomb-like structures. Zeolites have a network of aluminum, oxygen, and silicon atoms. So these three together they'll combine to form zeolite. Zeolites are nothing but what? Shape selective catalysts. Shape selective catalysts. Depending on the molecules, because of their honeycomb-like structures, the adsorbed bits will get absorbed on the zeolites. So that's why they are nothing but what? Shape selective catalysts. They are called as shape selective catalysts. Zeolites are shape selective catalysts. Zeolites have a network of aluminum, oxygen, and silicon atoms. Zeolites are used as catalysts in petrochemical industries for cracking and isomerization. Isomerization means just like forming an isomer, and cracking. Cracking means pyrolysis. Pyrolysis means breaking up of an organic molecule into a giant organic molecule. Pyrolysis. Pyrolysis, I'll write the spelling properly. So what is pyrolysis? Pyrolysis is nothing but what? Breaking up of a giant organic molecule into smaller ones. This is called cracking or pyrolysis. So this is used in petroleum industries. Next. So what is zeolite? A zeolite is nothing but shape selective catalyst. And before going to that, I want to discuss more about zeolites. So a zeolite named ZSM5, a zeolite named as ZSM5. This is the name of the zeolite. This is a model of zeolite, that is ZSM5, which is available in the market, which is used to convert gasoline into petrol. Sorry, alcohols into gasoline. Gasoline means petrol. So which is used to convert alcohols into gasoline. So this is the example they'll ask in the examination. So what is the zeolite name? It is called as ZSM5. So zeolites are shape selective catalysts, and these are used in petrochemical industries. So a zeolite name called as ZSM5, which is used to convert alcohols into gasoline. Please note this point. This jettism 5 is a geolate which is used to convert alcohols into gasoline or petrol. So that's why it is used in petrochemical industries. I hope it is clear. Next, now enzyme catalysis. What are enzyme catalysis? So enzymes are proteins of molecule of high molecular masses. Enzymes are protein of high molecular mass and complex nitrogenous substances. So every enzyme must contain nitrogen. So they contain nitrogenous substances. So these are produced in living organisms. They are very effective catalysts and catalyze most of the biochemical reactions in a living organism, even our body also. So these are known as biochemical catalysts. Simple words, what are enzymes? Enzymes are called as biochemical catalysts. So enzymes are protein molecules of high molecular mass and complex nitrogenous substances. So they contain nitrogen also. These are produced in living organisms. They are very effective catalysts and catalyze most of the biochemical reactions in a living organism. These are also known as biochemical catalysts. I hope it is clear. So now we are going to discuss more about enzymes in this topic. Examples of enzyme catalysis. Inversion of cane sugar. So cane sugar means C12H12O11 on hydrolysis in the presence of an enzyme called invertase. Here the enzyme is called invertase. It is acting like catalyst and it is a biochemical catalyst which converts the cane sugar into glucose and fructose respectively. So this is an example of enzyme catalysis. Next, one more example. This glucose in the presence of zymase. So conversion of glucose into ethyl alcohol. So the zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. So 2 moles of ethyl alcohol and carbon dioxide. And conversion of starch into maltase also. The diastase enzyme converts starch into maltase. So starch on reaction with water in the presence of diastase enzyme converts into maltose. So these enzymes they'll ask in the examination. So here this process is called as this invertase enzyme is first starting with, so I'll write it here, fermentation of alcohol or molasses. So fermentation process, it is used to prepare ethyl alcohol. It is used to prepare ethyl alcohol. So fermentation of alcohol also you can say. And anyway, you will study that in organic chemistry. So here my aim is nothing but to study about enzymes. So for sugar cane, that is sucrose, in the presence of invertase, it forms glucose and fructose. Glucose in the presence of zymase forms ethyl alcohol and carbon dioxide. The conversion of starch is nothing but its formula is molecular formula C6H10O5 taken n times. And conversion of starch into maltose. Maltose formula is C12H22O11. This is also just like sucrose. But the arrangement is different. Maltose and sucrose, they are nothing but same molecular formula, but they have different structures like glucose and fructose. Glucose also C6H12O6, fructose also C6H12O6. But the arrangement of molecules is different in glucose and fructose. That linkage is different. That anyway you'll study in organic chemistry. Here our point is only discussion about enzymes. So I'm discussing with enzymes only. So what are the enzymes we have? Invertase, zymase, and diastase. Next, conversion of maltose into glucose. So maltose in the presence of maltase, an enzyme which converts into glucose again. The decomposition of urea in the presence of UES. UES is a catalyst which is nothing but it forms ammonia and carbon dioxide. So UES is an enzyme again. In stomach, the pepsin enzyme, here this is about biochemical catalyst. So this is about our human body. So in stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. So all these points they'll ask only for JEE main students. It is a little bit difficult, but it is not so difficult. Also, you have to just remember this. Whereas for bio students, it is very easy because they'll study everything about human body. So in stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. So conversion of milk into curd also is an enzymatic reaction brought about by lactobacilli enzyme present in curd. So it is due to the presence of lactobacilli enzyme present in curd which makes the conversion of milk into curd. I hope it is clear. So all these examples, they'll definitely ask in the objective exams. So that's why be careful and read properly. So important, all the PPTs, whatever you're given for you, all the whatever PPTs I'm just going to discuss with you in all the classes is very, very important. If you maintain that PPT as your classwork notes, 100% you can answer any question in that chapter in any competitive book. I hope you understood. Next. Now, what are the different enzymes and what are the enzymatic reaction and what is the source? So, invertase, it is present in, it is coming from yeast cell. It converts sucrose into glucose and fructose. This already we have seen. Next, zymase, it is also coming from yeast cell. So, it converts glucose into ethyl alcohol and carbon dioxide. Next, diastase, it is coming from malt. It is used to convert starch into maltose. Maltase, it is also coming from yeast cell, so it is used to convert maltose to glucose. UES, it is coming from soya bean. Soya bean means just like your meal maker, we'll call it as soya bean. It is used to convert urea into ammonia and carbon dioxide. Pepsin, present in stomach. It is coming from the stomach. The source is from stomach. It is an enzyme released from the stomach which converts proteins into amino acids. Next, characteristics of enzyme catalysis. It is highly efficient, highly specific, highly active under optimum temperature and optimum pH. Activity increases in the presence of activators and coenzymes, and activity decreases in the presence of inhibitors and poisons. So, the reaction using enzyme as catalyst is highly efficient and is highly specific in nature, and it is active under optimum temperature, that is room temperature, and optimum pH, that is acidic nature, neutralic nature, or acidic, slightly acidic and less neutral in nature. That is pH should be approximately less than 7, but it's not like more than 6 to 7, in the range of 6 to 7. So that's why we'll call it as optimum pH. It is neither acidic nor basic nor neutral. So activity increases in the presence of activators and coenzymes. Activity decreases in the presence of inhibitors and poisons. For example, the pH of human body is 6.4. So 6.4 human blood is nothing but it is slightly acidic in nature, slightly acidic in nature. So that's why I told you this is optimum pH. Next, efficiency of the catalyst. Enzymes are highly efficient as catalysts. If enzymes are highly efficient as catalysts, they increase the rate of reaction by 10 to the power of 6 to 10 to the power of 8 times. Very, very important. So, due to the presence of enzyme, the activation energy is very, very low, and they increase the rate of reaction by 10 to the power of 6 to 10 to the power of 8 times. Very, very faster. So, due to the presence of enzymes only, the reaction takes place easier. What is highly specificity? Enzymes are highly specific in nature because a particular enzyme catalyzes a particular biochemical reaction, and the enzyme UES catalyzes the hydrolysis of urea only. It cannot be used for any other reaction. So it does not catalyze hydrolysis of any other amide, only amine. This is NH2CO NH2, that is urea only it is used. So that's why it is highly specific in nature. Enzymes are highly active at particular temperature known as optimum temperature. As I told you, the optimum temperature range for enzymatic activity is room temperature, that is 25 degrees to 35 degrees, that is 298 kelvins to 310 kelvins. So it is just exactly room temperature, almost. Exactly room temperature is 25 degrees C, and slightly more than that room temperature, the enzyme activity is more. Human body temperature is being 310 kelvins is suited for enzyme catalyzed reactions. That's why in our body so many enzymatic reactions takes place. The food we ate is converted into chemical energy, the chemical energy is converted into kinetic energy or muscular energy, so that our body builds up. So human body temperature being 310 kelvins is suited for enzyme catalyzed reactions, which is highly specific in nature. The catalytic activity is maximum at a particular pH called optimum pH, which is in between 5 to 7, as I told you, 6 to 7. But exactly if you take, it is in between 5 to 7, optimum pH. So that's why highly activate optimum conditions. What are the optimum conditions? As I told you, it is room temperature, that is 298 to 310 kelvins, that is human body temperature. And next is the catalytic activity is maximum at particular pH called optimum pH, which is between 5 to 7. So these values are important for objective exam. Activators are coenzymes. The enzymatic activity is increased in the presence of certain substances known as coenzymes. Like we have promoters, here we have coenzymes. What is coenzymes? Just like promoters. So they will increase the activity of enzyme. They will increase the activity of enzyme. That's why they are called as promoters. Activators are generally metal ions such as Na plus, sodium ions, manganese ions, cobalt ions, etc. These metal ions, which when weakly bonded to enzyme molecules, increase the catalytic activity. As I told you, coenzymes are just like promoters in normal catalysis. So here the coenzymes will increase the activity of the enzyme catalyst. Amylase is in the presence of sodium chloride. Amylase in the presence of sodium chloride is very active. Sodium ions are catalytically very active because it makes amylase to do more activity. That is the reaction rate of reaction increases so fast. I hope it is clear. Next, inhibitors. Inhibitors means poison. The enzymes are inhibited or poisoned by the presence of certain substances. So due to the presence of certain substances, they act as poison and they will decrease the activity of enzyme. These inhibitors are poisonous, they will decrease the activity of enzymes. They will decrease the activity of enzymes. So the enzymes are inhibited or poisoned by the presence of certain substances. The inhibitors of poisons interact with the active functional groups on the enzyme surface and reduce the catalytic activity. Poisoners don't think it is just a bad thing. Actually, they reduce the catalytic activity. The use of many drugs is related to the action as enzyme inhibitors in the body. That's why whenever you get fever or cough, cold, etc., to make the action less, we have to use the drugs, that is nothing but medicines, so that they act as enzyme inhibitors in the body, so that the reaction will not take place faster, means the fever will be reduced, everything will be done. So I hope it is clear. So these are the inhibitors. Inhibitors means they are just like acting as poison by the presence of certain substances. So the inhibitors of poisons interact with the active functional groups on the enzyme surface and reduce the catalytic activity, clots, etc., fever, cough, cold, etc., whatever the disabilities in our body. So the use of many drugs is related to their action as enzyme inhibitors in the body. They will stop the growth. Next, very, very important mechanism of enzyme catalysis. It is nothing but it has two steps: binding of enzyme to substrate to form an activated complex. So first, the substrate means nothing but the binding of enzyme to substrate. Substrate is nothing but what? The reactants. Substrate is nothing but what? The reactants. So binding of enzyme to substrate to form activated complex. So enzyme plus substrate forms enzyme substrate. Step 2, decomposition of activated complex to form product. So this activated complex will change into enzyme substrate changes to enzyme plus product. So this mechanism is known as lock key mechanism, key and lock mechanism, because exactly it fits into the, that's why it is called shape selective catalyst. Enzymes are also biochemical catalysts and it is based upon lock and key model. So lock and key mechanism, you can just see here. So active site, these are the active sites, and exactly the substrate will be fitting into the active sites like this. Bonds in substrate are weakened and then they change into products, and then the enzyme will be as it is like this. So this is called lock key mechanism of enzyme catalysis. It is shown clearly in the picture. So this the grooves will be fitting exactly to the enzyme like this. So in the grooves of the enzyme acts as active centers, and the substrate, that is the reactants, will come and fit into the grooves of the active sites, so that it is just like lock and key position. So lock and key mechanism, after as the substrate are getting closer to each other, what happens, the reaction takes place and product is formed. Once the product is formed, they get dissolved from the enzyme, that is absorption takes place as well as desorption takes place. So finally they form products like this, it will take place. So the mechanism of enzyme catalysis is also called as lock and key mechanism. Next, application of catalysis in industries. First, Haber's process for the manufacture of ammonia. Finely divided iron, molybdenum as promoter, conditions 200 bars, high pressure, and 723 to 773 kelvins optimum temperature. Nowadays, the mixture of iron oxide, potassium oxide, and aluminum is also used. This is a preparation of ammonia by Haber's process. and the reaction as already you know. So nitrogen plus hydrogen combines together to form ammonia. This is the reaction. So this is called Haber's process, and this reaction is taking place as iron as catalyst, molybdenum as promoter. Conditions: pressure is high pressure, that is 200 bars, and temperature is optimum temperature, that is 723 to 773 kelvins, exactly around 550 temperature degrees C. Nowadays, a mixture of, instead of using iron, you can use iron oxide, potassium oxide, and alumina is used as catalyst. So any of this you can do. So this is the first application in the industry. I hope it is clear. Next process. Ostwald's process for the manufacture of nitric acid. So the catalyst is platinized asbestos. Temperature is 573 kelvins, optimum temperature. So in this method, we'll prepare nitric acid. So from ammonia. Ammonia in combination with oxygen in the presence of it gives nitric oxide plus water. So this nitric oxide combines with oxygen and forms nitrogen dioxide. Nitrogen dioxide and combining with water and oxygen forms nitric acid. So in this, the catalyst is platinized asbestos. So all these reactions are important. This is the second application of catalysis in the industry. Next, very important, sulfuric acid. Sulfuric acid is prepared. So by the usage of sulfuric acid, we can say about the standard of industry. So more the usage of sulfuric acid, high profitably the industry means it is manufacturing so many products. So by the usage of sulfuric acid, we can say about the standard of industry. So if they use sulfuric acid maximum, it is nothing but they are giving more product. That's why sulfuric acid is also called as king of chemicals. It is also called as what? King of chemicals. Why? Because based on the usage of sulfuric acid only, we can say how much productivity the industry is going to take. So how much productivity the industry is producing. So that's why this is the contact process for the production of sulfuric acid. So 2 moles of sulfur dioxide in combination with oxygen, it forms 2 moles of sulfur dioxide. Sulfur dioxide on combination with sulfuric acid again will form oleum, and oleum on hydrolysis forms sulfuric acid. Oleum on hydrolysis forms sulfuric acid. In this, the catalyst is most important here. The catalyst is platinized asbestos. The catalyst is what? Platinized asbestos or vanadium pentoxide, and temperature is 673 to 723 kelvins. So this is the usage of catalyst in industries. I hope it is clear. Next. So in this, we have completed up to catalysis now. The catalysis part is over. So in all these catalysis, they'll ask questions based on theoretical questions. That is, which are the following is catalyst in the preparation of ammonia by Haber's process? Why molybdenum is you acting as promoter? All these questions they'll ask. What is heterogeneous? What is homogeneous catalysis? Next, in this chapter, very, very important concept, that is colloids. We are going to discuss now. We're going to start colloids. It's a very lengthy topic in this chapter, and definitely you are going to get questions from colloids only, as well as adsorption. From catalysis you may get or may not get, but adsorption and colloids are most important topics in this chapter. So that's very important. Please listen carefully. So next topic in this chapter, we have colloids. What are colloids? Colloids are nothing but suspended particles in a solution. So colloidal state is a state of matter in which the particle size lies between 1 nanometer to 100 nanometers. Very small particles. That's why we call it as suspended particles in a solution. Suspended particles in a solution. Suspended particles in a solution are called colloids. So what are colloids? I hope you understood. So suspended particles are in a solution are called colloids. They are neither solutes nor solvents. They means solution means you'll be thinking whether they can be a solute or solvent, but they are neither solute nor solvent. Just they are suspended particles in a solution. They are called as colloids, and their size ranges from 1 nanometer to 100 nanometers. So the size of colloidal particles is in the range of 1 nanometer, that is 10 to the power of minus 9 meters, or 100 nanometers. 100 nanometers. So I hope it is clear. So very small size. Continuation of colloids. What is the true solution? A true solution, because in colloids means definitely we have to discuss about solution. What is a true solution? It is a homogeneous solution in which the particle size is less than 1 nanometer. A true solution is a homogeneous solution. Homogeneous means the what are the particles, they are uniformly spread in the solution. That's why it is called a homogeneous solution. Where what do you call it as homogeneous solution? If the particles are spread evenly in the solution, particles spread evenly in a solution, evenly throughout the solution, you can say throughout the solution, then it is called as homogeneous solution. Throughout the solution, if the particles are spread in evenly throughout the solution, it is called a homogeneous solution in which the particle size is less than 1 nanometer. It is less than 1 nanometers. The particles in a true solution are not visible. Only by means of spectroscopy, spectrometer only it can be visible. Example, solution of sugar in water. Sugar solution, after dissolving everything completely in water, if you see, you cannot see the particles of sugar in water, but you can feel the taste. I hope it is clear. This is called two solution. A two solution is a homogeneous solution in which the particle size is less than 1 nanometer. That's why we cannot see with our naked eye. By the means of microscope, powerful microscope or spectrometer only we can see it. Next, what is suspension? Heterogeneous mixture of two substances in which the particle size is more than 100 nanometers. It is nothing but the particles are visible to naked eye. This insoluble precipitate in a solution. If you take a solution in that whatever the precipitate is nothing but suspension. So the colloidal solution has a particle size range in between that of a two solution and a suspension. So this colloidal solution has a particle size range in between that of two solution, that is 1 nanometer, and a suspension that is 100 nanometers. So they can be visible to naked eye based on the size. So these 100 nanometer size particles can be visible with the naked eye, whereas 1 nanometer size particles are not visible to the naked eye. So on the whole, in a heterogeneous solution is nothing but heterogeneous mixture of two substances in which the particle size is more than 100 nanometers is nothing but a suspension. So particle size less than 10 to the power of minus 9 nanometer, that is 1 nanometer to solution, and colloidal solution 10 to the power of minus 6 to 10 to the power of minus 9 meters. So colloidal solution is the size, and suspension greater than 10 to the power of minus 6 meters. System homogeneous. True solution is always a true solution is always homogeneous, and a colloidal solution is heterogeneous. Very important. So a true solution is homogeneous, and a colloidal solution is always heterogeneous. Heterogeneous means the particle size is not uniform, and suspension heterogeneous. Next, visibility of particles not visible. To solution, the particles are not visible. Visible under an ultra microscope because they are also less size, but they can be visible under ultra microscope. Where suspension we can see by the means of naked eye because suspension is nothing but it is precipitate in a solution. Precipitate easily we can see. Precipitate means the which is not dissolved in the solution is called as precipitate, but it is not solute also. We'll call it as precipitate. And precipitate easily we can see by the means of naked eye. Nature of system, transparent, translucent, and opaque. What is translucent? Translucent means it has optical activity. It has what activity? Optical activity. That's why the solution is translucent. Nature of system is translucent. I hope it is clear. So what is translucent means it has optical activity. So colloidal solutions will have optical properties. So it can be visible only under a ultra microscope. So colloidal particles, what is the size range of colloidal particles? 10 to the power of minus 6 to 10 to the power of minus 9 nanometers. That's what 10 to the power of minus 6 to 10 to the power of minus 9 meters, not nanometers. I hope it is clear. Next. Differences between true solution, suspension, and colloidal solution continued. Filterability passes through both filter paper and parchment paper. True solution can be passing through filter paper as well as parchment paper, which is nothing but semi-permeable membrane. And colloidal solution passes through only filter paper but not through parchment paper. So this is nothing but colloidal solution. So passes through filter paper but not through parchment paper. Suspension does not pass through filter paper or parchment paper. Suspension cannot pass through either filter paper or parchment paper. So these are all the properties are very important. They'll ask in objective exam. So setting of particles do not settle down. Two solutions do not settle down because they are completely soluble. The solute particles are completely soluble, and colloidal solutions also do not settle down because in this also the colloidal particles are present, but they are soluble. And this is settled down because they form precipitate. As precipitate is present, they are settling down. I hope it is clear, just like mud. What is dispersed phase and dispersion medium? And now we are going to discuss more about colloidal solutions in this topic. So what is dispersed phase and dispersion medium? Colloidal solution is a heterogeneous system containing two phases. One is dispersed phase, solute, like, and in the solution we have solute and solvent. Like that, in colloidal solution we have two phases mainly. One is dispersed phase, another is dispersion medium. What is a dispersed phase? Solute like substances in the solution, they are called as dispersed phase, and dispersion medium is just like solvent, but they are not actually solute and solvent. So dispersed phase is nothing but solute particles like, and dispersion medium is nothing but solvent medium like. In the colloidal solution of starch, the dispersed phase is starch and dispersion medium is water. So water is big in quantity and starch is lesser in quantity. We can call it a solute and solvent. But as they are forming colloidal solution, it is not a true solution. So that's why this colloidal solution contains in the colloidal solution of starch, the dispersed phase is starch and dispersion medium is water. Just like less lesser quantity, lesser quantity is nothing but dispersed phase, and higher quantity is nothing but what? Dispersion medium. Higher quantity. So I hope it is clear. Just like solute and solvent, but we cannot call them as solute and solvent because it is a colloidal solution. That is nothing but suspended particles in the solution are called as colloids. They are no way related to solute and solvent, but they look like solute and solvent in the medium. So dispersed phase and dispersion medium. So in the colloidal solution of starch, the dispersed phase is starch and dispersion medium is water. I hope it is clear. Next, it is based on either physical state of dispersed phase and dispersion medium, nature of interaction between dispersed phase and dispersion medium, and classification of colloids is based on physical state of the dispersed phase and dispersion medium. So nature of interaction between dispersed phase and dispersion medium, and also types of particles of the dispersed phase. So based on these three factors, the classification of colloids can be done. So what are the different types of colloidal systems we have? Depending upon the physical state of the dispersed phase and the dispersion medium, 8 types of colloidal systems are possible. How many types? 8 types. All these 8 types are very important. They'll ask in the examination. 8 types of colloidal systems are possible. What are those? We are going to discuss now. That table is very important. So this table I told you very important. So these 8 systems of colloidal system. So what are they called as? Salts, etc. When a, when the dispersed phase is solid and dispersion medium is solid, solid in a solid, it is called as solid solution, and they are nothing but examples: colored glasses and gemstones. So in colored glasses and gemstones, the dispersed phase is also solid and dispersion medium is also a solid. Solid in liquid, that is sol. Example, plains, cell fluids, muddy water. So in muddy water, what happens? Mud will be there, that is sand will be there. Cell fluids also. Paints, in paints also solid is present. So if the dispersed phase is solid and dispersion medium is liquid. So in a paint, liquid is more than solid. So that is called a solution. Next is solid present in gas. If a solid is dispersed phase and dispersion medium is gas, example, they are called as solid aerosol. Example, smoke and dust. Dust particles are nothing but solids. They are present in the air. Air is a gas. So air is a dispersion medium and solid is the smoke and dust particles are dispersed phase. So that is nothing but smoke and dust present in air. So in air, what happens? Air becomes dispersion dispersion medium because it is more in quantity, and the dusty particles are smoke is the nothing but solid particles. They are nothing but called dispersed phase. Next, liquid and solid, they are called as gels. So liquid dispersed phase less amount and solid is more amount. Example, cheese, butter, jelly, toothpaste, etc. All these are called as gels. I hope it is clear. More systems we'll discuss now. So all this they will ask in examination. So please go to this table, very, very important. This table is very important. So liquid, they are called as emulsions. If a liquid is the dispersed phase and dispersion medium is also liquid, they are called as emulsions. Example, milk, hair cream, emulsion paint, etc. Next, liquid in gas. So if the dispersed phase is liquid and dispersion medium is gas, they will call it as aerosol. Solid aerosol, liquid aerosol. So liquid dispersion, dispersed phase is liquid, dispersion medium is gas. Example, fog, mist, cloud, insecticide sprays, etc. Next, gas in solid. So gas is dispersed phase and solid is dispersion medium. It is called as solid sol. And example, pumice stone, foam rubber, bread, etc. Next, gas in liquid, it is called as foam. Example, froth, whipped cream, soap, leather, etc. So these are all the different types, 8 types of here. In the first five slide, we are discussed about 5. Now we are discussing about 3. So total 8 types of salts are we have discussed. So what are the 8 types of salts? Emulsions, aerosol, solid salt, foam. And in that case, we have solid salt, liquid salt, etc., etc. Solid aerosol, etc. I hope it is clear. Next. Classification based on interaction between dispersion phase and dispersion medium. So based on the nature of interaction between the dispersed phase and the dispersion medium, that is the nature of interaction means either the attraction. Colloids are classified into 2 categories mainly. This is very, very important. Lyophilic colloids and lyophobic colloids. Lyophilic means solvent loving, and lyophobic means solvent hating. In other words, solvent loving and solvent hating. So what are lyophilic colloids? The dispersed phase particles are in attraction with the dispersion medium. Dispersed phase is in attraction with the dispersion medium. That's why solvent loving. And lyophobic means dispersed phase is not in attraction with the dispersion medium. That is called lyophobic colloids. So based on the nature of interaction between the dispersed phase and the dispersion medium, colloids are classified into lyophilic colloids and lyophobic colloids. So what are lyophilic colloids? We'll discuss now. So both are very, very important. So what are lyophilic colloids? Lyophilic colloids are the colloids in which there is high affinity between the dispersed phase and dispersion medium. As I told you, high attraction. That is why we'll call it as solvent loving. Solvent loving means high affinity towards between the dispersed phase and the dispersion medium. So both will have high affinity towards each other, so that they're very much close to each other. So example, starch solution, protein solution, etc. So lyophilic colloids are the colloids in which there is high affinity between the dispersed phase and dispersion medium. I hope it is clear. So this is called lyophilic colloid. Next we have lyophobia colloids. Lyophobia colloids are the colloids in which there is little or no affinity between the dispersed phase and the dispersion medium. So they do not have any affinity. That is the affinity, no affinity between, affinity means attraction, no affinity between the dispersed phase and the dispersion medium. That's why lyophobic salts are less stable than lyophobic salts. Lyophobic salts or colloids are less stable than lyophobic colloids. Sorry, lyophilic colloids, lyophilic salts, or lyophilic colloid. So, what are the examples? Gold salt, arsenic sulfate salt, blood, etc. So, all these are the examples. They'll ask examples also. Which of the following is a lyophobic colloid? Which of the following is a lyophilic colloid? So, gold salt, arsenic sulfate salt, blood, etc. are called as lyophobic colloids. I hope it is clear. Starch solution, etc. are called as lyophilic colloids. So examples are also important. Try to gather as many examples as you can from the textbook, NCRT book, as well as other competitive books. So here I have given only few. So you can please note it down. They will ask in the exam, lyophilic, which of the following is a lyophilic colloid, which of the following is a lyophobic colloid, and they'll give 4 options. I hope it is clear. So gold salt, arsenic sulfate salt, blood, etc. What are lyophobic colloids? They are called as solvent hating in general words, and they are called as solvent hating colloids. And here there is no affinity between the dispersed phase and the dispersion medium. So these are called lyophobic colloids. I hope it is clear. Next, Differences between lyophilic and lyophobic colloids. This table is also important. High affinity between dispersed phase and dispersion medium are called as lyophilic colloids, and there is no affinity between dispersed phase and dispersion medium. Next, lyophilic colloids are prepared by direct mixing of dispersed phase and the medium, whereas they has to be prepared by special methods. And lyophilic colloids are very stable, as I discussed with you. It is very stable because there is affinity between dispersed phase and dispersion medium. So to break their solution, we have to use more energy. That's why they are very stable. And these are not very stable because there is no affinity between dispersed phase and dispersion medium. Hence, they are not very stable. And lyophilic colloids are reversible, and lyophobic colloids are irreversible. So all the differences are important. Next, they cannot be easily coagulated. What is coagulation or flocculation? That we'll discuss later on. So lyophilic colloids cannot be easily coagulated, and lyophobic colloids can be easily coagulated. And viscosity higher than that of dispersion medium, because both have affinity. Automatically, they have high viscosity, and viscosity is same as that of dispersion medium because there is no affinity between dispersion medium and the dispersed phase. So that's why viscosity of the dispersion medium is same. So the viscosity of lyophobic colloids is nothing but it is same as that of dispersion medium viscosity. Next, surface tension is lower than that of dispersion medium because as they have affinity towards each other, so surface tension is very low, and surface tension is same as that of dispersion medium. I hope it is clear. Next, based on the type of particles of the dispersed phase, colloids are classified into, as we discussed, mainly three topics in colloids. So, first, based on the interaction nature of interaction between them. Second, based on the type of particles of dispersed phase and dispersion medium. And third one, based on the types of particles of the dispersed phase, colloids are classified into multimolecular colloids, macromolecular colloids, and associated colloids. All these three are important. What are these three? Based on the types of particles of dispersed phase only, they are called multimolecular colloids, macromolecular colloids, as well as associated colloids. So what are these? We are going to discuss now. Very easy, very important also. So what are multimolecular colloids? Multimolecular colloids are formed by the aggregation of the large number of atoms or small molecules to give the particles of colloidal range. So these are the colloids formed by the aggregation, means joining. Together they combine with each other. Large number of atoms come together or small molecules to give the particles of colloidal range, that is 1 nanometer to 100 nanometers. Example, a gold salt contains particles having many atoms of gold. Sulfur salt contains many molecules of acid. I hope it is clear. So the sulfur salt contains many molecules of acid. So this is nothing but multimolecular colloid. It is formed by the aggregation of large number of atoms. So gold salt contains particles having many atoms of gold. Sulfur salt contains many molecules of sulfur, acid molecules. I hope it is clear. This is called multimolecular colloids. Next, macromolecular colloids. Some of the polymers, polymers like polyethylene, polyethylene, etc. Some of the polymers, when dissolved in a suitable solvent, very important. Some of the polymers, when dissolved in a suitable solvent, give rise to a particles of colloidal range. If you dissolve a polymer in a suitable solvent, they form particles of colloidal range. These colloidal particles solutions are known as macromolecular colloids. Example, solution of starch in water, protein solution, enzyme solution, etc. So all this called as macromolecular colloids. Macro means when dissolved when the polymers some of the polymers when dissolved in a suitable solvent, which give rise to particles of colloidal range. These colloidal solutions are known as macromolecular colloids. Protein solution, starch in water, enzyme solution are the examples of, etc. The examples of macromolecular colloids. Next, associated colloids, very easy. These are the colloids formed due to association of large number of molecules to form particles of colloidal range. So many molecules will join together to form a large number of molecules to form particles of colloidal range. These are known as micelles. You will find this in soap, micelles. Micelles are nothing but what? Associated colloids. What are micelles? They are nothing but associated colloids. At lower concentration, the solution will be a two solution. At very low concentration, the solution will be a true solution. As the concentration increases, the particles aggregate and form the colloidal solution. Example, soap solution. As the concentration increases, the particles aggregate and form the colloidal solution. That is nothing but lather. We'll call it as lathers. Lather is nothing but what? Low concentration and high concentration. So at lower concentration, the solution will be a two solution. As the concentration increases, the particles aggregate and form the colloidal solutions. So micelles are nothing but associated colloids. What are associated colloids? They will join together. These are the colloids formed due to association. That is nothing but combining together of large number of molecules. Association of large number of molecules to form particles of colloidal range. These are called as associated colloids. I hope it is clear. Next, what is critical micelle concentration? So what is CMC? Critical micelle concentration. The minimum concentration. This is also very important. They'll ask in the exam. So based on colloids, you'll get a lot of questions in all the competitive exams. And I told you in the starting only, from this chapter, definitely you'll get 2 or 3 questions from every exam. For every exam, either you like JE mains, JE advanced, or NEET, or any other competitive exams like BITS, Pilani, etc. So in all the entrance exams, these from this chapter definitely you'll find 2 or 3 questions, and that 2 questions are also coming from absorption or colloids. That's why very important, and it's only a memorizing topic, and only less logic is there. So the minimum concentration of the electrolyte required to form ionic micelles is known as critical micelle concentration. Ionic micelles means they'll form partial charges, that is partial positive and partial negative. For example, in soap, what is soap? Sodium salt of fatty acids. Soap is nothing but what? Sodium salt of fatty acid are called soaps. Sodium salt of fatty acids are called soaps. In that they form Na plus and acids. What are the formula of acids? CH3CO minus. So CH3CO minus, like, so they form sodium salt of fatty acid means, example I have shown you. So they form ionic micelles. So the minimum concentration of the electrolyte required to form ionic micelles is known as critical micelle concentration. For the soaps, the CMC is 0.001 molarity of the soap solution to 0.0001. That is in the form in the range of 10 to the power of minus 3 to 10 to the power of minus 4 molarity. The concentration. This is called critical micelle concentration. So the minimum concentration of the electrolyte required to form ionic micelles is known as critical micelle concentration. What is soap? It is nothing but sodium salt of fatty acid is called soap. Sodium salt of fatty acid. Fatty acid means this will be taken n times. Very big giant molecule. On dilution, the micelle turns into individual ions to form the two solution. So if you dilute, the micelle turns into individual ions to form the two solution. So the first soap, the critical micelle concentration varies from 10 to the power of minus 3 molarity to 10 to the power of minus 4 molarity, or 0.001 molarity to 0.0001 molarity. I hope it is clear. So this is called critical micelle concentration, that is CMC. Next, what is craft temperature? Craft temperature is also important. The minimum temperature required for the micelle formation is known as craft temperature. At what temperature the micelles are formed, it is nothing but what? It is called craft temperature. As I told you, micelle is an associated colloid. It is what? Associated colloid. And to form the associated colloid, whatever the temperature is required at that formation is nothing but what? Craft temperature. So at CMC and craft temperature, the ions associate to form ionic micelles. So under these conditions, the value of corrugative properties will decrease rapidly due to association. Very important. Due to association, they'll join together. So many aggregate molecules will join together to form a micelle. As I told you, we are going to explain that micelle also. So under these conditions, the value of colligative properties will decrease rapidly due to association. So this is called craft temperature. And the minimum temperature, usually it is room temperature, required for the micelle formation is known as craft temperature. I hope it is clear. Next, mechanism of Myceli formation. Mechanism of myceli formation. Soap is sodium or potassium salts of long chain fatty acids, as I told you already. It is nothing but a sodium or potassium salts of long chain fatty acids. When soap is dissolved in water, it dissociates into two parts mainly. Very, very important. Just please note it down. Everything is clearly mentioned here. If you read textbook also, you may understand, but it is more easy for you to understand every student. That's why I have written the notes like this and made a PPT. So soap is sodium salt or potassium salt of long chain fatty acids. When soap is dissolved in water, first what happens? It dissociates into two parts. That is, one is polar carboxylate ionic part. Carboxylate ion means COO Na plus, CO minus and Na plus. This is called polar hydrocarbon part, which is ion carboxylate ionic part. That is so many molecules CH3COO minus Na plus. This is called carboxylate ion. So many CH3COO taken n times. CH3COO taken n times. CH3COO CO like this. Only one CO is there, but this is a big chain of molecules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbon atoms here. So polar carboxylate ionic part, which is hydrophilic, and non-polar hydrocarbon, which is hydrophobic. So it dissociates into two parts. One is hydrophilic part and hydrophobic part. So what is hydrophilic part? This is called the hydrophilic part. That is polar carboxylate and is nothing but hydrophilic part, and Na plus is our hydrophobic part. So as they form two solutions, in a soap solution at low concentration, the ions are on the surface with polar carboxylate group with water and hydrocarbon chain part staying away from it. At CMC, the ions are pulled into the bulk and aggregate. The non-polar part will be at the center and the polar part is projecting outside. The spherical aggregate is known as ionic myceli. See how it forms the diagram you can see here. This is the carboxyl ions which are going towards the, see, when they form in water, they form associated molecule, they form myceles. And one is hydrophilic part. This hydrophilic part will combine with water and forms a myceli. And this myceli will go and attack dirt on the clothes. It will go and attack the dirt particles. These myceles will go and attack. Myceles attacks the dirt particles and makes it clean. So this is called action of soap. Cleansing action of soap. The cleansing action of soap is due to ionic myceli formation. The dirt on cloth is oil-based particles. When soap is applied on dirt, the non-polar part, here you just underline this, which is the non-polar part, which is the giant organic molecule. The non-polar part gets connected with it and the polar part projects outside. The ionic myceles are formed with the dirt at the center and the ions of soap surround it. That is, sodium ions are surrounding it. When a stream of water is passed, it will wash away the myceli along with the dirt. So the myceli particle along with the dirt, that is low concentration, both will go off so that the cleansing action of soap is being discussed. Next continuation. So you can see here soap molecules, soap solution, dirty cloth. So when in this first stage, what happens? This soap molecules form a myceli and they attack on the dirt part. And then the dirt part along with the soap molecules will escape away from the cloth. So that it becomes, first they'll attack the dirt part. This is called formation of myceles. I'm writing here. Formation of myceles. So attacking of that part and then it forms like this. I hope it is clear. So this is about colloids. In this topic, we have discussed more about colloids. So more about colloids also we discuss more. And in this, what we are discussing in this session is very, very important. First, we discussed about first catalysis, that is enzyme catalysis, and also shape selective catalysis. and then we have started colloids. So we'll discuss more questions on colloids in the next session. I hope it is clear. So I'm ending this session. So I'm ending this session. All the important notes we have done. So very, very important. So please take care. Thank you. So I'm ending.